Dr. Loïc Lannelongue. He's a research associate from University of Cambridge, and the title of his talk is Addressing the Carbon Footprint of Computational Science. Thank you, Loïc.
Thank you very much. So hi, everyone. This is going to be a bit different from all the other talks today, a lot less math, I guess. But hopefully the goal today is to kind of show you where the carbon footprint of computational science, particularly but science in general, comes from, and hopefully show you that there are lots of stuff we can all do to make research more sustainable without getting in the way of innovation. Full disclosure, my background is math and machine learning, so anything I'll talk about today, I'm fully guilty of. All right, so just a bit overview of what's been done, especially in the past couple of years around the environmental impact of academia in general. The focus in general is mostly about conference travel, just because the numbers are a bit mind-blowing. A fun fact is climate change scientists are the ones flying more than other scientists. And something not surprising is the carbon footprint is highly correlated with seniority in academia. Now, conference travels, there are lots of numbers, but there are quite a few fields who have had a bit of fun, like calculating the carbon footprint of their main conferences. So there's one about the Geophysical Union, and it's in 1 week they used the same as, well, it's basically the same carbon footprint as the entire city of Edinburgh in the week, or a life science or neuroscience conference, and they found that it's just as much as 1,000 medium-sized laboratory for a year. So other numbers like that, but it's just to keep the idea in mind. But basically, yes, a 1 week in-person conference when you have scientists flying from all over the world, it's basically the same as either a city for a week or like a very large research institute for a year. They compared it for the virtual event, and that's equivalent to a single return trip from Liverpool to the middle of France. No big surprise here. There was some really interesting work done by the field of astronomy, where they tried to look at the entire carbon footprint of the field, not only conference travels, but they also look at computing and also field work, because they do have a lot of that. And they found that the carbon footprint of an Australian astronomer is 40% greater than someone who doesn't do astronomy. Now, if we focus on healthcare, because it really is the focus of today, there's this really interesting review by Gabriel Samuel that was actually released just earlier this month. And if you want to really see what's done in the field, I won't try to summarize everything today, but the main conclusion is what you would expect. The fact that there is a carbon footprint of healthcare-related research, especially the digital aspect of it. And when you try to cure disease in the first place, it's great if you can try not to contribute to the problem at the same time. So it just needs something that needs to be accounted for. And obviously, healthcare-related research will also help to cure the effects of climate change. So it's not to say this shouldn't be done, not at all. Another point that's really interesting is the fact that the population that will suffer the most from the development and the research into these latest treatments are also the population that will benefit the least from the same developments. So something to keep in mind. This is just a related publication, and that just puts out some key principles for sustainable research, but I'll basically cover those in our work as well. Now, if we focus on artificial intelligence, actually, it was almost the first field to feel a bit guilty about the carbon footprint of their work, just because, especially language models, they're so big and they run for days and days that it become a bit of a topic. So you may have come across Emma Strubble's article that says that, what training one model is as bad as 5 cars during their lifetime. So it got picked up by quite a few headlines. So it was interesting. There's been a bit of work in that. It's all very much dedicated to natural language processing, though, just because it's the biggest model, but it doesn't mean the other fields don't have a problem. The stochastic parrots article is also really interesting, and they make exactly the same point as Samuel before, which was the fact that the population benefiting the most from Alexa or Apple Siri are also the population well, it's the opposite. People benefiting the least from those are the population suffering the most from climate change. Well, this paper also triggered the end of the entire ethics team at Google, so that was a bit of a problem. Anyway, so we do have a problem, and it doesn't mean we need to stop doing science, but hopefully we can all agree that there is a problem out there. If we try to see why it matters, 100 megaton of CO2 per year is a rough estimate of the total annual carbon footprint of all data centers. For context, it's as much as the entire American commercial aviations. Now, not all of that is science, and not all of that is research, of course. So I looked at XSEED. I don't know if any of you know it. Basically, it's a collaboration of institutions in the US, and they just put together their high-performance computing resources. They group it so this way they can mutualize resources, and it's more efficient. And they publish usage statistics, which is really good. The numbers are a bit mind-blowing. Like 24 million compute hours used every day on the network. And that's just one consortium of, a few scientists in the US. And we can see how it's split by field. So it's very much, everyone is concerned. And I guess AI kind of like trickles in every field. So, we do have very significant computing use. So yeah, there's a bit of a problem. Actually, not everyone agrees. So that's there's been quite a few papers put out by Google AI teams explaining that no, there is no problem. Please stop looking. Everything's fine, and it's actually going to save the world. Yann LeCun is the head of AI at Facebook, and unsurprisingly, he agrees. I very much wonder why. And yeah, so we do have a problem. It doesn't mean that AI is not going to solve the problem. They're probably not going to solve it, but it can definitely help. There's great effort using machine learning and computer vision to tackle climate change, but we do have a problem. All right, now if we just dive in slightly to try to see where the carbon footprint is coming from. So we can split it. We talked about travel, and that's an easy one to quantify, so I won't talk about it more today. Anyone doing wet lab related research, there's obviously a lot of source of carbon footprint here. Offices in general, lighting, heating, things like that. And then if we zoom in on computing, we can divide between two types. We can divide between day-to-day computing, everything, watching Netflix, scrolling on Instagram, things like that, or intense computation, when you have one either using HPC facilities, or you leave a computer to run for 2 or 3 days using quite a lot of resources. So now I'm going to focus on these mostly. It doesn't mean the other aspects don't have impacts, but lots of people have done a lot more work on that, and we had to pick one topic for today, so that's the one. Again, for the sake of today, all that is the same. So it doesn't matter if you do computations on your laptop, or if you use HPC facilities or virtual machines. It doesn't matter. All the principles will be applicable here. And yeah, with all the research we've heard about this morning, hopefully there will be bits and bobs that are relevant to all of you. So when we talk about the environmental impact of computing, we can actually split it in 3. First, we have the life cycle footprint. So that means, extracting the raw material, manufacturing the device, using the device for its entire lifetime, and then disposing of it. And when we talk about consumer devices, so your phone, your laptop, your tablet, 70 or 80% of the footprint is only due to manufacturing. Which means that just keeping your devices for longer is the the best thing you can do to reduce this aspect. Because if you try to charge it only every other day or something like that, you're only acting on the remaining 20%. Now, if we look at hardware that's put in data centers, the share is lower. It's only 10 to 20%, because obviously the hardware is used a lot more in the data center. That's the whole point of HPC facilities. But still, it probably would be good to take into account sustainability when deciding when to renew hardware. Where nowadays, HPC hardware is mostly renewed based on when the warranty expires, because then it's more expensive to repair than to replace. Then there's long-term data storage. I mean, with all the imaging data we've seen today, I'm sure many of you are familiar with the issue. Obviously, storage, it doesn't use as much energy as a GPU, but it's for long periods of time. So when we look at the energy bill of a data center, we have half of the power is dedicated to servers and 10% to storage, and the rest is overheads, cooling, lighting, things like that. But 10% of a big number remains a big number. So yeah, it's hard to put an exact number, but based on like some manufacturers' assessments and things like that, kind of the order of magnitude you can remember is 10 kilograms of CO2 to store 1 terabyte of data for a year. So yeah, doesn't mean we shouldn't store data, because obviously it's probably beneficial to store data rather than rerunning the experiment and with all the associated carbon footprint, but data that you're never going to use, probably not worth storing. And finally, we get to probably what you're thinking about when we talk about the carbon footprint of computing is actually the impact of running the computation themselves. And that's where it can get a bit complicated, because where does it come from? Is it the power consumption of the computer and what to include, what hardware to look at, what about energy production? This is why it can be quite complicated, and why for a long time people just didn't look at it at all. But actually we'll just simplify it, and that's pretty much as hard of math we will have today, so a bit easier. If you look at the carbon footprint, it depends on two things. It depends on how much energy you need. So that depends on your hardware and on your algorithm. And then it depends on what's the carbon footprint of producing the energy you need. And that mostly depends on the energy mix of your country, because most data centers are just connected to the main power grid. So we'll just focus on the first one. So if we just look at the carbon footprint of the energy needed, you feel free to ignore that. If you want the details of that, we kind of put all the details in the paper, but feel free to it's just what you would expect, running time, the cores, the memory, and the efficiency of the data center. A very easy example for running time, some of you may be familiar with these tools, but basically it's just a bunch of bioinformatic analysis. If it doesn't ring a bell, just ignore it. But the two blue bars at the start is genome-wide association studies. And it's exactly the same analysis using the V1 of a popular tool, Bolt LMM, or using the V2.3. And there's no magic here. It just means they made the tool so much more efficient that obviously you save on running time, but you also save on carbon footprint. And just shows that, no one likes updating a software, because, when you update it, it kind of breaks everything and you have a whole sorts of dependencies that go wrong. But sometimes, even if the saving in running time is not business critical for you, just think that maybe it also impacts carbon footprint. So yeah, using optimized code is a great way to do it. And the power usage efficiency. So that's just what measure the overheads, so cooling mostly. And that's where, for example, cloud computing is quite good, because they put a lot of resources into making the data centers more efficient. We came across this really funny example, so we put it in our paper, because we looked at weather forecast, and it turns out the data center was based in Reading in the UK for the European data weather forecasting system. And probably partly because of Brexit, probably other reasons, they decided to move it to Italy in Bologna. And in the press release, what they said is, look, it's a great move because we're getting more efficient hardware, more efficient data center, and we're actually moving to a data center with a lower PUE. But because of what we said before, it also depends on where the energy is coming from. And because the energy in the UK is greener than the energy in Italy, although it's a more efficient data center, the move is actually increasing the carbon footprint of the process. Unless they power the data center there by solar panels or something. So there are these kind of weird catches that sometimes either people don't get or decide not to look at. Yeah, so it just shows that the computing facility does play a big role, and if you have any choice in that, you can probably either promoting more efficiency in your local data center or choosing more efficient ones. All right, so we sorted with that. We saw how to estimate the energy use. Next is how to look at the carbon intensity. So it's called carbon intensity, which is like the carbon footprint of producing electricity. And there just is a massive discrepancy between countries. So if you run, so that's just for a selection of countries. It's actually from 2020, but I mean, the ranking hasn't changed that much. If you run exactly the same analysis in Switzerland compared to doing it in Australia, you will emit 74 times more CO2 equivalent for the exact same task, just because you locate it differently. Switzerland is based on hydro, Australia is based on coal. Australia also suffers a lot from climate change. doesn't make a lot of sense. The UK is here, so not bad, but also not the best. If you want to see, if you're running your computation in a particular country in a particular part of the world, and you want to see how it's doing, Electricity Map is a really handy website. They really show live in real time where the energy is coming from, and it also breaks it down so you can understand what's going on where you are, and it shows exports and imports and stuff like that. So it's quite an interesting browse. So yeah, realistically, because of this kind of 74 times kind of multiplication factor, just moving data center, if you can at all, because obviously there are lots of regulations, especially working with health data. You can't kind of just take your data and put them on the cloud or just export them into another country. But if you have any possibility for that, well, this is just the single most impactful thing you can do because of these discrepancies between countries. All right, so that's it. That's actually not that hard. So that just shows if you can try to estimate the carbon footprint of your work and also report it. We live in a world controlled by data. If there's no data, there's no problem. So the more we kind of show that it's just a number. It's like the financial cost. No one would start an experiment and not know how much it's going to cost you at the end of the day. So it's the same thing. You can do a little cost benefit analysis and say, okay, well, is it really worth rerunning this experiment for the 100th time, hoping I will get slightly different hyperparameters this time? I mean, I've done it. Here we are. So this formula is great, but it takes a bit of effort. So what we did, it's a collaboration with Michael Inouye from the Department of Public Health and Jason Greeley, who is based in Australia. We created an app to make the whole thing a lot easier. So basically, you can just plug in the parameters of your computation and where you're located, what hardware you're using, and so on and so forth. And it gives you the carbon footprint. It gives a bit of context, how long it would take a month to absorb that much carbon and things like that. So yeah, feel free to check it out if you're interested. And then the question was, do people actually care about it, or is it just us having a bit of fun doing it? And it turns out people do. So, I mean, it's not millions of people, but also we're talking to computational scientists, which is a bit of a niche. And it was really interesting to see a steady increase. We have about something around 200 people using the app every week now, and all over the world, which was also a big part. We wanted to see if we could reach a wide audience. So that's just nice to see that, yes, scientists did care about it. It was just, they were just lacking the tools to do it. And then we went back to bioinformatics, because it kind of started all from that. We're just wondering what's the carbon footprint of our work, and then we realized there was no way to know it. So we had to build the tool and everything first, which instead of taking 2 days takes something like 2 years. But we went back to bioinformatics. So some of you may be doing this kind of analysis here. I'm not going to dive into each analysis. It's just if you're interested, but the best is probably to check out the papers where we detail what we're doing. But that's just an overview of basically an overview of the field of bioinformatics. So all the we sampled popular tools being used, and we used a public benchmark and papers saying how long it took them to train it and things like that to look at the carbon footprint of each. The interesting conclusion here is that some tools like genome-wide association studies or molecular simulations do have a large carbon footprint because they need to run for a very long time using lots of resources. But some have very small carbon footprints as well. So it's not to say all analyses have a massive impact, but some definitely do. All right, and then there's the fact that all these numbers is if you run the analysis once, but I'm sure many of you know it never works the first time. Then you need to debug it, then it breaks again. And if you do any kind of machine learning, you need to tune hyperparameters. So obviously for that, I'm sure you're familiar with things like Bayesian methods for hyperparameter tuning, rather than going for brute force approach where you try to take completely random combination of your parameters. So these are ways to limit that. But yeah, the best trick is be stingy. And again, don't over tune it at some point. If you feel like it's not going to improve it, it's probably not going to improve the results. And that's probably the only message, if you have one message to take from that today, is that computing is not free, which is something that's hard to believe, especially, I guess, being in Cambridge. Computing time on the either on CSD3 in the clinical school or different HPC facilities is well, I'm sure PIs will disagree here, but it's virtually free. Like there's lots going around. It's rarely the limiting factor. And at the end of the day, you rarely feel like, except if you're very large task, but normally you just run it. So that's the only message here. Doesn't mean we shouldn't do science. Obviously not. There's like so much exciting research presented today. Doesn't mean we should slow down or we shouldn't do some experiment. Just be mindful and know that it's out there to be a bit more responsible. Interestingly, so our work, not only our work, obviously, but partly triggered all these research, so you'll recognize some I mentioned earlier. But it was really nice to see that when we started working on it, there was nothing out there. And it was actually even a struggle to find reviewers for our initial paper because it just wasn't really a field. But now in the past couple of years, there has been a lot more work and research published, and some fields doing a bit what we did for bioinformatics, so looking at the carbon footprint of tools used in their field, especially in physics, which was really good to see. So what can we do? Well, I've tried here to summarize some of the main advice. I've walked you through most of that already. So after publishing all that, we said, well, okay, what we need is something that's easy to read, not another paper that no one's going to read. So we put together 10 simple rules. So it's a work also with Alex Bateman, who's based at EBI. And yeah, so if you want something easy to read, you can check this out. It's very much just 10 rules. I talked about keep, prepare, reuse. I talk about efficient data centers, the importance of like estimating your carbon footprint before running an analysis, or just having an idea where you're getting into and then acknowledging it after it. Taking into account sustainability, choosing your computing facility, both in terms of having an efficient data center, but also where is it located, and using optimized code. So what do we still need? Well, probably a lot of things, but I've just picked two. The first one is to reduce frictions further. I mean, we all hate anything that makes our life a bit difficult, especially computer scientists, I guess. So this app is good, and it does its job, and it's a good way to have a rough estimate. But if you, for example, if you run 100 different experiments, and each experiment is going to run for a slightly different time using slightly different hardware, obviously you can't put everything in the app, or you could aggregate and things like that, but it's not ideal. You can see the limits of having an online app in this case. The main motivation for the online app was to say, okay, we don't want anything that need to be installed because people don't like to install stuff in their pipeline. So that's why it was good to have something online where you don't need to touch. But then obviously the limitation is it's not very customizable and it's not very integrated. So there has been some packages, some Python packages in particular, already integrated, and that can track your code. But yeah, we still need to reduce these frictions. And then we need more transparency, and that's really much from everyone. So institutions are not always very keen to communicate about the carbon footprint of what they're doing and what their research teams are doing, even though the scientists usually don't care. Same thing for data centers. They like to say they're efficient. They don't like to say it if they're not. Cloud providers are very much using efficiency as a marketing argument, but that's very much what it is still today. So, if you start digging in and trying to find the details about each data center, not all the information is available. Hardware manufacturers and obviously us as scientists, we just need to be a bit more transparent about what the impact of what we're doing. So with this idea of saying, okay, well, reduce frictions further, I was like, okay, well, ideally, that's what I want. That's something where you just put it on your, if you're using HPC facilities, so you're using it through the command line. And we said, okay, well, just saying what's my carbon footprint, and I say, well, for example, for the year of 2020, and then it gives you the carbon footprint. So I had a bit of a play with it on the Cambridge CSD3, and I made that. Admittedly, it's a lot less pretty than the app, but also it's a lot more accurate. So I'll just zoom in here. Basically, it's very easy because the HPC facilities are just logging everything you do just to be able to charge you. So what that's doing is just scrolling through, the logs, pulling everything, aggregating stuff together, and just calculating summary stats, and then using the same formula the online app is doing and the same data to calculate carbon footprints. The good thing is it can give you a lot of detailed statistics. A lot of them I would gladly ignore. How many of my job failed. I didn't want to know that. if you tend to like over allocate memory, we've all done that. Or let's get 100 gigabytes of memory just to be safe. I don't want it to be crashing halfway through. And it breaks it down by like CPU, GPU, and everything. So that kind of works. It's still kind of a beta version, just because obviously the downside of making something a lot more custom is it very much customized to the platform you're using it on. So Cambridge CSD3 is using Slurm. Some of you might be familiar with it. It's just a workload manager, which is widely used. So this should work on any HPC facility that uses Slurm. Hopefully, it probably won't. So I've tried it on here. I've tried it in a couple of other places, but if you're interested at all to give it a go, or if you want to give it, because basically when it's installed on the platform, it doesn't do anything. It's basically a bash script. So it's very limited. It's very light, but it needs to be installed by every kind of user groups, because it's not something that's installed widely across the university. But so it's all on GitHub with instructions on how to customize it for your own platform. But if you want to give it a go, do get in touch. I'd be very happy to help you. And I'm trying to see if it can work on many different platforms. So, the more the merrier. Now, I talked about transparency. This is a bit of an old example, but that was quite good. So Jonathan is a lead scientist at Regini, and they work on GWAS, so the same genome-wide association study I kind of took as an example before. And they published this new tool that was supposed to be much faster, and they used that as a side benefit. They said, look, it's much faster, and on top of it, it saves a lot of carbon, which is great. Interestingly enough, Twitter thought it was offensive content. But if you accept the danger, it just shows you the savings. But yeah, so that's the kind of very simple thing. They just put it in the annex, and it just shows that it's in this case, it's an added argument for their model. What we try to do in the lab in general is just when we have papers that are based on heavy analysis, we just at the end in the acknowledgement, we just put a rough estimate of what the carbon footprint of the entire research presented is. And when we can, we try to offset this carbon footprint. And I'll talk about offsetting a bit more in a minute, but that's the kind of painless acknowledgement that can help raise awareness. If you're interested in lab sustainability in general, because obviously I've very much focused on computational, on the computational side of things here, do check out. This is a really cool podcast. They talk with a lot of scientists on how to make science more sustainable. It's focused on wet lab, but not only. We actually had we did an episode with them about the impact of computations. LEAF, some of you may be familiar with. It's an initiative driven by UCL. That's a way to help wet labs to be more sustainable. So it's a really great initiative, and we're actually now working with them to include the computational side. So hopefully in the next few months, there will be kind of an equivalent, but it will be LEAF, but it will also apply to dry labs. So they have some kind of awards like bronze, silver, gold, things like that. And if you're interested, especially for PhD students or master's students, there are lots of green lab initiatives, which are usually driven by students in their respective institutions. So yeah, I took a screenshot of Twitter because they're all on Twitter. Do check it out. There are lots of initiatives like that. Now, I'm just going to talk very briefly about offsetting, because offsetting, for those of you who don't know, it just means you're buying carbon credits. So it's saying, okay, I emitted 1 ton of CO2 equivalent, so I'm just going to make up for it by sponsoring maybe tree planting that are supposed to make up for this carbon footprint. It's a touchy topic because, well, it's tempting. It's an easy option. It just means you're paying instead of reducing your carbon footprint. Also, it's based on a lot of assumptions. So when you're sponsoring, for example, planting trees, the assumption is, okay, you're planting 2 trees. These 2 trees will stay exactly where they are for the next 60 years, surrounded by the same environment, with the same environmental conditions. And in this case, yes, they will offset your emissions within their lifetime. You can see how many things can go wrong in 60 years. So that's why it's a bit tricky. And offsetting should very, very much be a last resort process. So, you've done everything you can to minimize your carbon footprint, but there will be some carbon emissions that's just not possible to avoid. So then you say, okay, well, then you can try to offset what's left, but very much last resort. Try to go through certified charities or companies. So Carbon Footprint is one of them, but basically they have a whole standards that they need to follow that ensure that as much as possible that what you're buying will make up for it, and usually try to offset many times more. So, if you think you emitted 1 ton of CO2, maybe try to offset for 10 to account for this kind of side effects. Oh, that's just a fun fact. Is those stripes I use at the bottom and that are on the online app are made by Ed Hawkins, who is a scientist at Reading University. And these are really starting to catch up. And actually, that's something from this morning. The Reading Football Club is using their stripes, which are the climate. It basically shows the evolution of temperatures through the years. And that shows the evolution of temperature on the sleeve in Reading for the past, I don't know how many years. So anyway, thought I would put it in. Yes, so I'm just going to, thank all our collaborators in Cambridge and at MWBI. And if you want to reach out about the app or about anything I've talked about today, I usually post on Twitter when I post updates. The app gets updated every once in a while, and just shoot me an email. Thank you. And I'll go. Oh.
Thank you, Loïc.
There was a slide after that.
Are there any questions, or have you got any more?
No, that's fine. There was like a summary slide.
Right.
It doesn't matter.
Any questions? Very different topic, but probably open up like research topics or research projects for you.
Thanks. It's a very interesting topic, the carbon foot. And I just want to suggest what's the best practice to use high performance computing facilities. So we do run a lot of jobs in the high performance computers. But I think probably we need to look at how the carbon footprint will be.
Yeah, I mean, usually, data centers are quite efficient ways. HPC facilities are quite efficient for that. So it's probably better to use HPC facilities than to do it with a desktop on your with a desktop computer on your desk. There's always the question of whether to use cloud computing or favor your local data center. And the only two arguments for cloud computing: you can usually pick the location of your data center. So obviously, if you're doing research in Australia, then yes, cloud computing is probably a good way if you can do it, because then you can do your computation in Switzerland, like the example, or somewhere in Europe. Other than that, their data centers are on average very efficient because they're pouring enormous amount of money at making them more efficient because it's just saving them money. It doesn't mean all the data centers are efficient. Usually when it's advertised, the PU is advertised is very much a world average or kind of a local average. So you can imagine that a data center in Iceland doesn't need as much cooling as a data center in Austin, Texas, for example. But the Cambridge data center is actually very efficient, surprisingly, because it's a local one, not a big cloud computing facility. But no, HPC is good.
Thank you. Are there any other questions? Yes.
Thank you for this very interesting talk. This 100 megatons that you showed, was that globally or for?
No, globally. Yeah, globally for data centers.
Yeah.
It's as you imagine, it's a very difficult number to come by because so many data centers, so many facilities. So it's very much like a rough estimate, and estimates range from anywhere from 50 megatons to probably 500 or 600 now. So 100 megatons is probably a lowish estimate, and that doesn't really include Bitcoin.
Okay. Yeah, obviously we should bring that down as much as possible, but I was quite surprised that it was so low, because global emissions are like 50 gigatons. So it's 0.2%, and McKinsey estimates the contribution of machine learning to the global economy above 1%. So it's 5 times more CO2 efficient than the average contribution.
No, I mean, it's the when we looked at conferences, the same thing. When we saw that actually doing online conferences, it has a carbon footprint, but it's so small compared to doing it in person. So yes, of course, using HPC compared to running a factory based on coal all day is infinitely better. I think the argument here is to say, and that's what the last IPCC report was all about, is to say we can't really afford to only act on the biggest contributors. And it's very much a case of reducing everything we can. But yes, compared to many, many other sources, it's probably still a net positive overall. Can just be probably more positive. I don't know.
Yeah, totally agree. Thank you.
Are there any other question? Yes.
Thank you so much for this interesting talk. I was wondering, you just at the beginning stated shortly about traveling. So what would be your suggestion for conferences?
It's quite interesting. Actually, Alex Bateman has a, so he made a talk recently, and he kind of has a strategy where he just like put a budget. So, you know, there's these budgets going around. So we're supposed to be at about 2.3 tons per person by within a few years to keep global warming in check, or about 3 tons for now, something like that. So you can still travel and kind of say, okay, well, maybe if you fly once a year, you're probably still going to stay within these boundaries. We were actually talking about that at lunch. There's this new, you may have come across the Cambridge University new guidelines about conference travels that kind of gives you a lot of examples, and they are quite sensible. The idea is to say, make sure you get the most out of it. So flying to the US for a 30-minute talk, if you're only doing that, well, it's probably not worth it. So it's very much like a personal decision. There's also the fact, and the guidelines are quite good at that, they're split based on seniority. So, a well-established scientist probably won't get much out of giving just a 10th talk on the same topic. Well, like a young scientist, yes, it will make a massive difference for their career to go over there and meet with people. So I think we need to be a bit sensible and just say, okay, well, take the train whenever you can. So we can take the train pretty much anywhere in Europe, which is just, I didn't put the numbers up, but it's really easy to find them. It's just amazing the difference between, I mean, just flying is very bad. That's in terms of carbon footprint. And we tend to underestimate like the orders of magnitude between flying and taking the train. So yeah, I mean, taking the train is a great one. It doesn't mean we can't fly, because obviously you can't take the train to the US or things like that. But just keeping it to when it's really worth it, not when, and just seeing when it can be replaced by Zoom. But I mean, I'm glad I'm here in person today, but didn't fly here.
Thank you. It seems that many people are looking for the recommendations from you. You've given some qualitative recommendations. I'm looking for some quantitative recommendations. You have quantified the footprint impact of different computational tasks. And has anybody or have you built like mathematical models to quantify the impact, and then also try to conduct scenario analysis about different strategies so that you can actually make more qualitative recommendation about the different strategies?
Not really, partly because it's really hard. When I talked about transparency,
everybody's doing mathematical modeling.
I know.
You can do that too.
Well, partly because it's really hard to have data about it. So when we did our survey of bioinformatics, for example, to measure something for GWAS, just because it's what I talked about, we had to crawl through papers, and most papers, they don't tell you for how long, when you publish an analysis, you didn't say I trained for like 12 hours and 30 minutes, because most people consider that to be irrelevant in a paper, and they don't say what hardware they're using. So actually, like people doing the analysis, so like all of us in this room, we are the best place to measure the carbon footprint of our own field. But it's really hard to do it as an outsider for another field, because my only way to do it would be to rerun analysis, but that's a bit silly to try to reduce carbon footprint and just run a lot of analysis just to show that it's bad. So the way for that to do it is and that's what some people have started to do, is to say, okay, well, my small field, for example, medical imaging in these kind of images, this is, you all know the tools that are commonly used in your field. And so you have ideas about how long it runs on hardware. You probably have runs that you can use the logs of. And yeah, that's just the way, and everyone in their field can do it.
I hope you will give a different answer in few years, 20 years. Well, I think it's more difficult to get medical data, financial data, than the data you would like to have. So
we'll work on it.
I think you will get there. Thank you very much.
Thank you.
Right. So we finish our session. Thank you, everybody, and also to the two wonderful speakers. I think according to the timetable, we have a tea and coffee break. Thank you.